All right, this is the handout for the slope fields homework. So let's read the direction here. It says sketch the slope field for each of the following differential equations, then find the general solution analytically. And for problems 4 through 6, find the general solution first, then the specific solution that passes through the given point, and state the domain for that solution. So we're just focusing on 1 through 3 in this video. So we have our differential equation, dy over dx is equal to 4 minus y. Remember, your differential equation is used to find these individual slope segments on your slope field. So this is what you want to fill in. So you want to look for some properties here. This differential equation is only looking at y values, doesn't care about the x value. So if you look at what's going to happen here, any value, any point on this line is always going to have the same y value, right? All these is y is equal to 4. All these have y values of 3. All these have y values of 2. So if the differential equation is only looking at the y value, then it makes sense that every slope on this line will be the same. Okay, so let's start with the easiest one here, is y is equal to 4. If y is equal to 4, then 4 minus 4 is equal to 0. So we're expecting at y equals 4, we're expecting that the slope is going to be 0. Okay, and if y is equal to 5, 4 minus 5 is negative 1. So every point here will have a slope of negative 1. So I just drew short line segments to represent a negative slope, estimating a slope of negative 1 as best as I can. And here, y equals 3. Plug 3 in for y. 4 minus 3 is 1, so this is a positive 1. Plug in 2. All these will have a positive 2. So we see that the slope is going to become steeper and steeper, right? If I plug 1 in for y, 4 minus 1 is 3. So we want to draw a line segment here with the slope of positive 3. Okay. And here, y equals 0, plug 0 in for y, so all these ordered pairs will have a slope of 4, and then 5, and then 6. So we begin to see a shape that we can use to match with the solution. So let's look at let's solve the differential equation and see if we can match this picture with the solution graph. Okay. Let's separate the variables. We're going to solve this differential equation. So y is on the left, everything else on the right. So dy over 4 minus y. We have to go through u substitution because this will produce something other than just a 1 for our derivative. Okay, so let the u value be 4 minus y. Derivative, du over dy, is negative 1. Okay, so we got to be careful here. 4 goes to 0, but negative y produces a negative 1. dy is equal to negative du. Make our substitution, so we get negative integral of du over u is equal to integral of dx. So the left side we get negative natural log of absolute value of u is equal to x plus c. Negative natural log of 4 minus y is equal to x plus c. We want to take the exponentiate both sides, but we first need to deal with this negative, so I'm going to move this negative over to the right side first. And then once I have that, now I'm going to take the exponentiate both sides, which will allow me to get this 4 minus y from out from under this natural log function. So then I can bring down the 4 minus y. Here, this is e to negative x times e to the negative c. E to negative c is a constant, so I just pull that in front. Solve for y, I get negative y is equal to c e to negative x plus minus 4. And so y is equal to negative c e to negative x plus 4. So c is just any constant, but if you plug this in your calculator, okay, you can plug 1, 2, or just leave that as a 1. Plug this in your calculator, and you're going to get a graph that either is going to be increasing or decreasing depending on whether that c value is a positive or a negative. Okay, and if you compare this general graph, all these potential parent graphs, okay, with this graph, you're going to see that there's a lot. You're going to see that this graph is going to match with the form of this graph, with the flow of this graph, right? You see that this represents where the graph is increasing, but it's going to start leveling out in slope, just like over here and we can think of this as an asymptote that is never going to reach. Now, I forgot to mention that I made the graph a little bit higher here so that I can actually see so I can see the behavior of the slope above the y=4 line. So I know the initial graph doesn't go that high, but I went that high just to show the similarities there. Okay, let's look at number 2. We have a differential equation, 3x squared. So we know that 3x squared, we can use ordered pairs here to plug in so that we can identify each of these individual slope segments. You know that if x is 0, your slope will be 0. So when x is 0, that's going to be where everywhere on the y-axis will be where slope is 0. And we're just going to get variations of positive slopes. No matter what x value we plug in, we're always going to get a positive value. So we saw this from the notes but from a different perspective. But here we can create the graph as we move further and further left. We're just going to get more higher and higher y values for slope. And that's the same thing going to happen here. So if you see this graph, it's going to represent this x cubed that we're eventually going to find. So if we find the solution for this differential equation, separate the variables. Y is on the left, x is on the right. So dy simply becomes y, 3x squared becomes 3x cubed over 3, which is x cubed plus c. So we have a family of functions. So you see this family of function that is going to be represented by the slope field that you see. Okay, number 3, this is similar to a problem that you saw from the previous notes section. So we separate the variables. First we can plug in ordered pairs. We see that any point on this x-axis is going to be where slope is undefined. So then we just simply plug values in. We see that anywhere on the x-axis, on the y-axis, will produce values of 0, so slope of 0, and just variations of positive slope above the axis and variations of negative slope below the x-axis. And if we solve this differential equation, we're going to get y squared equals 2 over 2 is equal to negative x squared over 2 plus c. Multiply through both sides with 2, and we get y is equal to y squared is equal to negative x squared plus 2c. Take the square root of both sides. 2c just becomes, represent that with just c. And if you plug any variation of negative x squared plus c, or any constant here, negative x squared plus 1 or negative x squared plus 3, plus or minus, your positive would be where the graph is above, and negative square root will produce values that's below. So if you look at these two graphs, it's going to represent you see the shape formed by this differential equation, by the slope field.